Hello everybody. In this video, we're going to learn about matrix inverses for 2 by 2 matrices. Now, matrix inverses are going to give us another way to solve linear equations. You've previously learned how to solve a system of equations by converting it to an augmented matrix and using row operations to calculate row-reduced echelon form. After this particular lesson, you'll learn another way to solve it, starting with the matrix equation form and calculating something called the inverse of a matrix. But before we dive into that, let's take a close look at something you've known how to do for a while, solving a simple equation like this: a times x equals b for the number x. So these here are all numbers. They're not vectors, they're not matrices, just numbers. Now I know a lot of you are going to jump and say, x equals b over a, done. But let's take it slowly, one step at a time. So starting off with the equation, a times x equals b, we need to remove a somehow. We don't physically pick it up and move it to the other side. What we need to do is undo multiplication by a. To isolate x. We do that by multiplying by a inverse. And if we do that on the left-hand side, then, well, the golden rule of algebra says we must do the same operation to the right-hand side. So we'd multiply both sides by a inverse. Now, when it comes to multiplication, a inverse is really the fraction 1 over a. So in both cases, we're multiplying both sides by 1 over a. 1 over a times a on this side gives you the number 1. The a's cancel out, and you have 1 times x. On the right-hand side, you could multiply this out. The b appears in the numerator, and then you'll have the fraction b over a on the right. And 1 times x, well, 1 is like an identity element. Multiplying x by 1 does not change its value. And so on the left-hand side, we're left with x. So the solution to this equation is x equals b divided by a. Now we're going to use a similar process to solve matrix equations. It's important to keep each one of these steps in mind. We have to figure out what the corresponding step would be in the context of matrix algebra. So first, we're going to need something called an inverse matrix. We'll write it with the same notation, the superscript -1, and the way we'll define the inverse matrix, the way we'll eventually calculate it, is by looking at this defining property. Any matrix times its inverse should give us the identity matrix. Remember, at the end of the last video, we introduced the identity matrix. It's the matrix 1, 0, 0, 1. And this identity matrix, if you multiply anything by the identity matrix, it does not change its values, similar to the way 1 times x is always equal to x. If you multiply the matrix ABCD times the identity matrix, you'll get ABCD. And it even works for a matrix vector product. If you multiply the vector xy times the identity matrix, the result will once again be the vector xy. And so, before we actually get into the formula for the inverse matrix, let's see how we'd use it. So if you have an equation like this in matrix form, right, the coefficient matrix times your vector of variables is equal to some constants, p and q. Let's give each one of these a name. Let's call the matrix A, B, C, D. Let's call the vector with the variables v. That's what we're going to solve for. So we want to isolate v on one side of the equation by itself. This vector of constants, p, q, let's call that vector w. So we could rewrite this matrix equation using these new symbols. Matrix A times vector v equals vector w. Now, following the same steps as before in normal algebra, we would start by multiplying both sides by an inverse matrix. Right? We'd have to figure out what the formula is in order to do this in practice. But assuming that we do know how to calculate an inverse matrix, A inverse times A should give us the identity matrix. So we don't have to actually multiply these out. We just know it will be the identity. And the identity times any vector v, well, is just that vector v again. And v, remember, that contains the variables x and y which we're trying to solve for. So the solutions for x and y can be calculated with this matrix vector product. It will be the inverse matrix A times the vector w. Right? And that could potentially go even quicker than calculating row-reduced echelon form. Whether it's quicker or slower, it is always good to have more than one way to solve a problem. And check your answer. Okay, so how do we figure out the inverse formula? Well, we're going to use algebra. Algebra is great. So let's say we have the matrix A, that's the matrix A, B, C, D, and the inverse matrix, we don't know it yet. Let's just write it as P, Q, R, S. The one thing we do know about a matrix, an inverse matrix, is A inverse times A must equal I. So what we'll do is we'll take this equation and we'll try to solve for these values, P, Q, R, S. We'll try to solve for those in terms of A, B, C, and D. Right? And if we can solve for these variables in terms of the numbers that we know, that will give us a formula for the inverse. So we can multiply these two matrices together. Again, we get some dot product patterns appearing here. And we know that this must be equal to the matrix 1, 0, 0, 1. So what we could do is separate out this into four equations. Right? This top left entry must equal this top left number. This top right entry must equal this top right number. The bottom left entry must equal the bottom left number. And the bottom right entry must equal the bottom right number. So that actually gives us four equations and four unknowns. The unknowns are P, Q, R, and S. And so the goal is to solve for P, Q, R, and S. Actually, it's a lot easier than it looks. There's a lot of variables here. But if we want to solve for P and Q, we just need the first two equations because they're the ones that involve P and Q. In fact, to solve this, I'd actually start with a second equation and solve it for Q. Right? Move P times B to the other side. So we'd have QD equals negative PB. Then to solve for Q, divide by D. That tells us what Q is. Once we've solved for Q using that second equation, we could plug it into the first equation. Right? So we'd have P times A plus this expression for Q times C equals 1. If you clear the denominator, multiply everything by D, get this expression, then factor out a P, and then, so you'll have P times a quantity, AD minus BC, and then you can divide through to find that P equals D divided by the quantity AD minus BC. Once you know P, you can plug that into this equation to solve for Q. The great thing is we've got a D in the numerator and a D in the denominator, so those cancel, leaving you with a negative B in the numerator and the same denominator as before. Similarly, you could go through and solve the second pair of equations. You'd find these expressions for R and S. Right? And so that gives you the formula to calculate an inverse. We can simplify it a little bit, so we're going to do that to hopefully make this formula easily memorable. So if you're given a matrix capital A with entries A, B, C, D, then the inverse of that matrix is given by this formula. Now notice that all these terms have the same denominator. So our first step is to factor out this fractional part to make the formula more readable, kind of like scalar multiplication. we're factoring something out from every term of the matrix. In this case, it's 1 over AD minus BC. And what we're left with is, well, the original numbers from the matrix just rearranged a little bit. Right? The A and the D have switched positions, and the B and the C have both become negated. Right? So to calculate the inverse of a matrix, you can switch the numbers in the A and D positions, you can negate the numbers B and C, and then multiply everything by this fraction. But also, this denominator here, we've actually seen that before. It's been a little while, but when we were calculating cross products, do you remember that in front of the I, J, and K terms, we would have a little 2x2 grid of numbers? And what we would do is calculate A times D minus C times B. And that gave us the entries of the cross product. This is the same thing. A times D minus B times C. Right, so this expression, it comes up a lot when we're working with matrices. It's called the determinant of a matrix. And sometimes it's written as DET of A. Right, so the determinant of a matrix, at least in the 2x2 case, is A times D minus B times C. One other important thing to note is that something could go wrong with this formula. If A times D minus B times C, if that determinant is equal to 0, then you're dividing by 0, and you know you can't do that. It causes mathematics to become inconsistent if that were allowed. So if the determinant of a matrix is 0, then there is no inverse. There is no A inverse. Not all matrices have inverses. And that's maybe not too unexpected. The same thing is true for ordinary equations, right? You can't solve all equations, right? If we tried to solve 0 times x equals 3, that wouldn't have a solution either. So just as something to keep in mind, not all matrices have an inverse. It's determined by the determinant. Okay, we should definitely do some examples, and of course, figure out how to check your answers. So remember, I'll just keep this up at the top of the slide as an easy reference. If your matrix A, capital A, has numbers A, B, C, and D, then the inverse matrix is 1 divided by the determinant, A, D minus B, C, times the matrix D, negative B, negative C, A. So for example, to find the inverse of the matrix 2, 1, 6, 4, the inverse matrix is 1 divided by 2 times 4 minus 6 times 1. Right, so that's going to be 8 minus 6, so that's a half. And then these numbers get rearranged. The 2 and the 4 switch places. The 1 and the 6 become negatives. And all these numbers get multiplied by 1/2. So 4 becomes 2, negative 1 becomes negative 1/2, negative 6 becomes negative 3, and 2 becomes 1. So this is the inverse matrix to this. The way to check is if you multiply a matrix times its inverse, you should always get the identity matrix, because that's how inverses are defined. Plus, it's good practice with matrix multiplication, so here we go. Let's take the inverse matrix and partition that into row vectors. Let's take the original matrix and partition that into column vectors, then do some dot products. For the top left entry, 2 times 2 minus 1/2 times 6, that's 4 minus 3, which is 1, that's good. The top right entry, 2 times 1 minus 1/2 times 4, it's 2 minus 2, which is 0, also good. For the bottom left entry, negative 3 times 2 plus 1 times 6, negative 6 plus 6, that's 0. And the bottom right entry, negative 3 times 1 plus 1 times 4, negative 3 plus 4 is 1. So sure enough, you do get the identity matrix. Let's do another. In this next example, capital A is the matrix 3, 6, 2, 5. To calculate the inverse matrix, we have 1 over the determinant. The determinant is 3 times 5 minus 2 times 6. So that's 15 minus 12. That's 3. So the inverse is 1/3 times the matrix. So you'll switch the 3 and the 5. We'll negate the 2 and the 6. And then multiply each one of these entries by 1/3. And you get the matrix 5/3, -2, -2/3, 1. And to make sure you're right, of course, once again, you could multiply A inverse times A and check and make sure you do get the identity matrix. All right, that's how you calculate the inverse of a 2x2 matrix. But remember, our ultimate goal is to solve equations. So how would you use an inverse matrix to solve an equation? Well, let's say you start out with this matrix equation. 2, 5, 1, 4 times xy equals 3, 6. And these are the sequence of steps that we would use. Basically, if you have matrix A times vector V equals vector W, then vector V is equal to A inverse times W. Right? We know what W is. We just need to calculate the inverse and then multiply. So if A is the matrix 2, 5, 1, 4, then A inverse is the matrix. Let's see, 1 divided by the determinant. So 1 divided by 8 minus 5, that's again 1/3. Switch 2 and 4, negate the 1 and 5. There's our inverse matrix. In this case, I'm not going to multiply through by 1/3 quite yet. I'll save that fun for later. Now to solve for V, which is the vector xy, that's going to be our inverse, which is 1/3 times this matrix times 3, 6. So just to avoid too many fractions, I often like to save the multiplication of the fraction for last. Keep working with whole numbers as long as possible. So multiplying this vector times this matrix, I'm going to do the matrix vector product. So partition that matrix into rows. We've got 4 times 3 minus 5 times 6. It's 12 minus 30, which is -18. For the bottom entry, -1 times 3 plus 2 times 6. It's -3 plus 12, that's 9. Don't forget about that fraction, that 1/3, which comes along. Some scalar multiplication here. Each one of these is getting multiplied by 1/3. 1/3 times -18 is -6. 1/3 times 9 is 3. So that is the solution to this equation. And if you want, of course, you can check by taking these values, plugging them in for x and y, and then just make sure that this equation is correct. One more example. I'd like to solve a system of equations using an inverse matrix. Right, so the first thing we would do is take the system of equations and convert it to a matrix equation. 5, 6, 4, 7 times vector xy equals vector 2, 8. Calculate the inverse of this matrix, and you'll find that that's 1/11 times the matrix 7, -6, -4, 5. And then we multiply this inverse matrix times the vector W. Right, so again, partition. 7 times 2 minus 6 times 8. Right, and in this case, I'm going to go ahead and multiply that by 1/11 there. And then -4 times 2 plus 5 times 8. It's -8 plus 40 is 32, and then multiply by that 1/11 there. And so this is your solution to this system of equations. As always, it's good to check. So plug these values into here and here, and make sure that you get the numbers on the right-hand side as expected. Okay, and we all know you learn math by doing math. So here's a problem you should try solving. And so in this case, I'd like you to use an inverse matrix. So find the inverse of this matrix, 2, 2, 3, 5. And then xy is going to be that inverse times this. You should be able to check, right? Make sure that when you plug in x and y, that the values turn out to be what you're expecting. If you're really bored and you want some more practice, you could even use the augmented matrix equation to solve this as well, to triple check your answer. All right, have fun doing math. Thanks for watching.